Easier to use combinatorics to find theoretical probability rather than listing and counting all the equally likely outcomes. Combinatorics include the fundamental counting principle and ways to count permutations and combinations. Some of you, I'm sure, were pretty fed up with problems 10 through 12 yesterday. You sit there and do your random thing and you keep track of it. And it's not that it's difficult, because it's not. It's just tedious, keeping track of all of that stuff. So if there were a shorter, easier, faster way for us to do that, then we would obviously want to be interested in that. What are we going to do? So this says finding probability use combinatorics. What is the theoretical probability of being dealt exactly 2 sevens in a 5-card hand from a standard 52-card deck? So far I've been talking to you about how we're going to put what we want over the total. But when we start talking about combinatorics, it's not just what we want, it's going to be what we want and need divided by the total. And I'll explain what I'm talking about as we go through this problem. What you want is to get 2 sevens. That's what we want. What do you need? You need 5 cards in your hand. So if we look at this and say, I don't care when I get the sevens, it doesn't matter to me which numbers come first, I just want to get the sevens in my hand for some reason, I have to think, well, how many sevens are there in the deck? How many are there? There's 4 sevens. And I want to get 2 of them. So that's going to be 4 choose 2. But that's not all that's going to be in my hand. That's where the need comes in. While I have my 2 sevens, I can't just say, okay, stop, don't give me any more cards. I'm going to have 5 cards. So my want is filled. But the need part is, I need 3 other cards. But they can't be sevens, because remember, I need exactly 2 sevens. So how many non-sevens are in a deck of cards? 48. There's 52 cards altogether, and if we take those 4 cards out of there, those 4 sevens, now we're down to 48. And if I already got my 2 sevens, how many more cards do I need to have a 5-card hand? 3 more. So this right here is what I wanted. I wanted those 2 sevens, but I needed 48 choose 3 because I had to have 5 cards in my hand. Now the total would be countable. How many different hands are there to get when you're playing cards? Well, there's 52 cards. That's the total. And you're going to get 5. So notice on the top here, I didn't put any sign between those two. That's because both this and this, what I want and what I need, have to happen at the same time. These are going to be multiplied times each other. And then we're going to divide by that 52 choose 5. So if we wanted to, we could punch this in all at one time. We could put a set of parentheses on the top here, a set of parentheses on the bottom, and do that. But I guess I'm kind of old-fashioned in that too. I do like to see the individual numbers as I go through. So I'll usually find 4 choose 2 or think my way through 4 choose 2 and get that answer, and then 48 choose 3. So 4 choose 2, start thinking, that would be 4 factorial over 2 factorial and 2 factorial. So that'll be 4 times 3 divided by 2 times 1, or 2 times 3, which is 6. But when they start getting a little longer like this, most people will grab the graphing calculator to do those combinatorics anyway. So let me go ahead and remind you, we can put in 4 math probability, number 3, and we want 4 choose 2, there's our sevens. We still get 6. 48 choose 3, the numbers are starting to get a little big. That's going to happen with cards. So maybe we just give up and say 48, math, choose 3. And 52 choose 5 will also be big. So 52, math, choose 5. And we'll multiply and we'll see if anything is going to reduce here. So 6 times our 17296 divided by 25. Well, actually, we could just do divide by answer. That was 2 steps ago. I better just punch it in. 2598960. Math number 1, enter. And notice this is going to happen. That fraction was so large that the calculator says, you reduce it. I don't want it. So we could actually just use this one as a percentage and say it's approximately 4%. Or we could write down the numbers that we had. And even a start at doing the reducing would help the graphing calculator. So if these are both even, we definitely could try it too, and we'll get this down a little bit. But in the end, I think with a lot of these card problems, yep, I remember checking in the book, a lot of the card problems, they just give us percentages. But let's see what we can do. 103,776 divided by 2. Nine, 8960 divided by 2. We notice, okay, those are both even again. Give it another try. Now, at some point in this process, the calculators will become small enough that the calculator would actually do the reducing for you. So let's see if this is small enough now that the calculator will take it. $5,944. And I don't know why I put parentheses up there, but 649740. Nope, still won't take it. So we can go again. And the reason I'm showing you this is because on the MCAs, I know they do some reducing. And you just have to keep going with it. Oops. There we go. And we could still go by 2 again. So any of those answers on a multiple choice test, you could see up there. Again, you could keep going because both of those are divisible by 2 again. It just depends on what you see for your multiple choice answers. Then, the got it says, what's the theoretical probability of being dealt all 4 sevens in a 5-card hand? So let's think about what we want. What do we want to happen? What's the goal of your hand of cards? 4 sevens. How many sevens are there? There's 4. So you want them all. You're greedy. You want all 4 sevens. How many cards do you have to have in your hand? So how many more do you need? And what can't they be? They can't be sevens. So how many non-sevens are in the deck? 52 minus 4. We want one of them. And on the bottom, we already know what the number is going to be. The total is going to stay the same with cards, especially when we're talking about we've got this 5-card hand that we're dealt all the time. So again, with this one, you could do some of the math in your head. You could look at that 4, choose 4, and say, hey, wait a minute, isn't that going to be 1? It will be 1. 48, choose 1. Isn't that going to be 48 factorial over 47 factorial times 1 factorial? So all that will be left is 48. And then, like I said, we already know what 52 choose 5 is. We had to write that enormous number down. Back up here, And chances are pretty good, again, that the calculator is not going to want to give us the fraction answer to this. But we could certainly see what it is as a percentage. And most people want to know the percentages anyway. So we get here. And this one, the percentage is so small, because you're saying you're going to get all 4 sevens, for goodness sake. The chances that that happening are really, really low. That it went to scientific notation. And it's telling us over there in the right-hand corner that we need to move the decimal 5 places to the left because this number is so small. That's what that negative is for. So that means we're going to need 1, 2, 3, 4 zeros in front of it before we can even write down the 1, the 8, and I guess I'll round to 5 in the next position. So that's what we would have as a decimal. As a percentage, this is going to look really dismal because we're going to move it back 2 spots. Oops, 1.85%. The chances are pretty small. Does it happen? Yeah, it happens. You know, it's just probability. It will happen at some point. It's just, is it going to happen a lot? No way. Absolutely not. So theoretical probability, thinking it through with the cards, and I had mentioned that before, that hopefully, at least maybe on, I don't know, maybe your smartphone, you played solitaire before or something like that, so you know a little something about cards. And then the second set you actually have a little experience with back in geometry, because this is geometric probability. And generally we'll have dimensions or we'll have a picture to help us out with geometric probability. It says a batter's strike zone depends on the height and stance of the batter. So it's kind of interesting when you're watching baseball, you know, you've got different strike zones depending on whether or not you have a really tall batter or a really short batter when they go up there. So what is the geometric probability that a baseball thrown at random within the batter's strike zone, as shown in the figure below, will be a high inside strike? And like it says, one of the hardest pitches to hit. And that's because if you look at this, obviously the ball is coming in really close to the batter, and it makes it tough to hit. So we're saying if it's in the strike zone, what's the probability it's going to be in that little red portion right there? Well, what we want is the little red portion, which just happens to be a rectangle. And it's not one-dimensional because we've got length and width to it. It's two-dimensional. So we're going to need the area of that little strike area, high inside strike area, over the area of the entire strike zone. So area for the high and inside strike over the area of the entire strike zone. Because what we want is that little inside, high inside strike zone over the strike of the whole. Well, everything for the batter, I guess I'm thinking here, the whole strike zone for the batter. So without scrolling up there, I'm checking to make sure that everything's in the same units, that they didn't do some in feet and some in inches. And everything here is all in inches. And the little high inside area is 4 by 6. So the area of that is going to be 4 times 6. What will the area of, what numbers should we use for the area of the entire strike zone? 17 and 22. So we could do a little reducing if we wanted to here, or we could just go ahead and give them a percentage for this. Let's see what we get. We've got 24 on the top, divided by 17 times 22. There it is. And this was small enough that it did give us a fraction here. So it just reduced it by 2. So this would be approximately 6.4%. So it's definitely a higher percentage than getting our 4 sevens in cards. And that one, again, that's geometric probability. Sometimes they'll give you a picture, sometimes they'll just describe it to you, and you need to draw the picture, which brings us to this one. This one says we've got a batter's strike zone, 15 inches by 20 inches. You don't have this one?
No.
Well, what happened there? Well, you maybe don't need it anyway. Let's talk through it. The strike zone, it says, is 15 by 20. High inside strike, 3 inches by 5 inches. What's the probability that a baseball thrown at random within the strike zone will land there? What do you put on the top? Maybe I do need to have you write this whole problem down. 5 times 3, 3 times 5. In the end, it's going to be 15. What do you put on the bottom? 15 times 20. Well, that'll be 15. And down here, what's 15 times 20? We could do some reducing, or we could just punch it in, let the calculator give us our decimal that we can change to a percentage. Whatever we want to do. Comes out very nicely. 0.05, which would be 5%. 5 100ths, 1/20th, if we actually did the fraction. So usually when we're starting to do different and large totals with combinatorics, we kind of hand it over to the calculator. And in fact, when you look in the back of the book for your answers for some of these, they're not going to bother giving you the fractions anymore. They're just going to give you the percentages because it's easier at that point. All right, we did more with probability today. We talked about cards and with geometric probability, combinatorics and geometric probability. 4, 3, 2, 1, 0. How do you feel? Now, some of the card stuff, it may take you a little while to think through all of those numbers, but I think you'll do okay. So keep in mind, there are 52 cards. 4 suits, 13 cards in each suit, 4 of each kind of card in the deck. You should be okay. Oh, I know the other formula you need for this assignment is you need to know the area of a circle. Everybody remember how to find the area of a circle? Okay, so does somebody remember the formula for area of a circle? What is it? A equals pi r squared. Because they're going to give you a bullseye problem, which MCAs love, ACTs love the bullseye problem. Here it is. Here's the dimensions. Now find the probability. Remember, it's what you want over the total. So you'll have to use area for that, for the bullseye.